Hello there, this is Jude Socrates. Welcome to video number 40 for my lecture series in multivariable calculus, known as Math 5C at Pasadena City College. Wow, milestone, 40 videos, and we're not quite done yet. So in our last video, we started our study of space curves and the parametric functions, the vector functions that create these space curves. So today we're going to add on to that study. We created the unit tangent vector. We're going to create two more unit vectors. They will be the unit normal vector and the unit binormal vector to the curve at that point. But to see a better way to construct these two vectors, we're going to decompose the acceleration vector. So we're going to see all of that starting at page 369. So I will see you there. All right, so at the end of the last video, we saw a theorem that said that if a curve is on the sphere centered at the origin, meaning every point has the same constant distance from the origin, then the velocity vector is always perpendicular to the position vector at that point. Okay, so we're going to use that, apply that theorem to the unit tangent vector. Okay, and that might disturb you a little bit because, when we saw the picture, we drew the tangent vector at the point on the curve. Okay, so we're not drawing it from the origin. Okay, but this is where the beauty of algebra and calculus lies in. Okay, because it doesn't matter how we visualize something. If we can do the algebra or the calculus on it, we're good to go. So the unit tangent vector, from the name unit vector, it has constant length 1. Okay, so if we actually drew the unit tangent vector at every point on the curve from the origin, then they will lie on the unit sphere. Okay, so therefore, according to that theorem, the derivative of the unit tangent vector, its velocity, quote unquote, will be orthogonal to the unit tangent vector. Okay? Now, it's possible that that derivative is the zero vector. So if it's never the zero vector, we say that our function is smooth, right? So if the derivative of the tangent vector is again smooth, then we can create another unit vector where we take the derivative and we divide by its length, okay? And that is called the unit normal vector, okay? So, yeah, we have to take the derivative of the unit tangent vector, and then we have to find its length and then divide by that length, okay? So we can see the interpretation here below, okay? We have a derivative, as usual, is a limit of a difference quotient, okay? So from the unit tangent vector at t, we move by a little bit, by delta t. So now we're pointing in a different direction, but still a unit vector, unit tangent vector, okay? So we find that difference, and then we divide by delta t, which means it gets longer because delta t is going to 0. Divide by a small number, you're multiplying by something bigger, okay? So you get, this is the appearance of the unit normal vector. It has to be perpendicular to the unit tangent vector because of our theorem, okay? And as it turns out, it will be pointing inwards into the curve. All right, so in our last video, we already found the unit tangent vector to the helix, okay? Here's where it is, and yeah, we can take another derivative. So negative sine becomes negative cosine, cosine becomes negative sine. We can find the length of that vector. Don't forget the 1 over square root of 2. The length of this vector, cosine squared plus sine squared, square root, so the length is just 1 over square root of 2. In other words, this is already a unit vector. So when we divide by the length, we just get that vector that I was just noticing. Okay, so that is our unit normal vector. Okay, so notice something interesting. The z component is 0. Okay, so in other words, it's parallel to the xy plane. Okay, here is the unit tangent vector. Here is the unit normal vector. It's perpendicular to t, and it is pointing into the curve. Okay, so in particular, it's pointing towards the z-axis. Okay. All right, we saw this example from our last video. R of t is made of this quadratic, a cubic, another cubic. Okay, we found the position, we found the velocity. We look for the velocity at the point 1. Okay, so we got that constant vector. Okay, but if we tried to get the unit tangent vector at every point, okay, and not just at this one point, we're going to need the general length of this vector. Okay, we're going to have to square that and square that and square that. And I don't know about you, but I'm not really excited to do any of that. So if we were to directly find the unit normal vector for this made up example, yeah, it's going to be really messy. Okay, so the good thing is we have a better way to do it, and we'll see it very soon. All right, so something very similar and unpleasant happens when we try to do it also for Viviani's curve. Okay, so we found the velocity last time, and if you didn't notice, that looks like a double angle formula, doesn't it? Oh, here's another one. So that's really negative sine 2 theta. That is cosine 2 theta. That's still just cosine theta. So if we find the length, it's actually a lot cleaner. Sine squared 2 theta plus cosine squared 2 theta, that's just 1. Oh, but wait a minute, there's a plus cosine squared. If only it were a minus cosine squared, then we'll just get sine squared. But of course, life is not always simple. So yeah, that is our length. This is the tangent, the unit tangent vector in general. Yeah, do you want to take the derivative of this vector? Yeah, even though that square root is not as daunting as our last example, this is still going to be very messy. Okay, so you'll need the product rule for scalar products, and yeah, you'll have to simplify that, and then you have to find the length, and then you'll have to divide by that length. So yeah, unfortunately, it's not going to be easy. All right, so the key to finding a better way to find the unit normal vector is to decompose the acceleration. Okay, so remember, it's the second derivative of our vector function. Okay, so we know that the unit tangent vector is just the first derivative, r prime, divided by its length. So solving for r prime, we have magnitude of r prime times the unit tangent vector. Okay, so now I just mentioned the scalar product rule. We can apply it to this product in order to get the second derivative of r. Okay, so r double prime is the first derivative of this product. So according to the product rule, you get the derivative of the magnitude of r prime multiplied by the unit tangent vector, plus, leave this alone, the magnitude of r prime times the derivative of the unit tangent vector. Okay, but now we know that the normal vector is the derivative of the unit tangent vector divided by its length. So we can replace t prime with the magnitude of t prime times the normal vector. Okay, so what does this equation tell us? Okay, the acceleration is a multiple of the unit tangent vector plus a multiple of the unit normal vector. Okay, so that means that the acceleration is on the plane which is determined by the unit tangent and the unit normal vector. Okay, and this is called the decomposition of the acceleration into the tangential and the normal components. Okay, so this coefficient, that's a scalar, we're going to call that a sub t. It will still depend on the point. Okay, and this product is going to be called a sub n. Also will depend on that point. Okay, so what we're going to do is we are going to simplify. We're going to find simplified formulas for these two coefficients, okay, by doing two clever things. We are going to take the dot product of the first and second derivatives. We'll use it to find a sub t. And we're going to use the cross product of the same two vectors to find our a sub n. Okay? Now, to prepare for us to do that, don't forget a couple of formulas that we saw way back in chapter 1, where we said if you have two vectors u and v, then their dot product, which is a scalar, is the magnitude, the product of the two magnitudes times the cosine of the angle between them. Similarly, the cross product, that's a vector. But if you get the magnitude of the cross product, that's a scalar. We said that the magnitude of that cross product is the product of the two magnitudes of the vectors times this time the sine of the angle between them. Okay? And if you have a really good memory, these two were connected to each other using what we called Lagrange's identity. Okay, so I wanted to show you one more time what we're going to do before we actually do it. Okay? Where are we? We have the acceleration. We have expressed it as the sum of two vectors, our decomposition. Okay? We want to find this coefficient and this coefficient. We're going to take two things, a dot product and the cross product, and that is what will allow us to find the two coefficients. Okay? So when we go to the next page, this entire vector will be copied, and that is our acceleration. We are going to dot it with r prime, and then later we are going to cross it with r prime. Okay, so those are the two things that we're going to do. We're going to see this long expression, and that's what we'll plug into these two expressions. All right, so here's the first thing. This is the second derivative that I was just showing to you. We're going to dot it with the first derivative. Okay, there's a plus there, so we can apply the distributive property. Take the first vector, take the vector over here, dot it with the first vector, so that's this term, plus the vector here, r prime, dotted with this second vector. Okay, so now we have this dot product over here, and what have we got? Well, we'll apply the first formula, which is over here. We want this dot product, okay? But r prime and the unit tangent vector, wait a minute, didn't the unit tangent vector come from r prime? We just divided by its length, right? So therefore, the angle between them is 0. What's the cosine of 0? 1. Not 0, it's 1. So therefore, this first term, this dot product, we can write it as this coefficient times the magnitude of r prime times the magnitude of t times the cosine of the angle between them, which is cosine 0, which is 1. Okay? Now wait a minute. There's a second term over here. Okay? We have r prime dotted with this vector n. Okay? Now wait a minute. Not t, but with n. Okay. R prime is parallel to t, but r prime is perpendicular to n. Okay. So this time, what's the angle between them? It's 0. Okay. So therefore, there's a typo here. That should be the scalar 0. Ooh, bad mistake. I should correct that. Okay. Either way, it goes away. So all we get is this derivative of the magnitude times, where did these go? How long is the unit tangent vector? Unit tangent vector, length 1, and we said the cosine of the angle between them. is the cosine of 0, which is 1. Okay, so therefore, what do we want? We wanted this coefficient, right? So therefore, we can solve for it now as this dot product divided by the magnitude of r prime. All right, so now we're going to take the same vector and we'll cross it with the first derivative. Okay, and luckily that 0 vector is correct this time. So once again, we have a distributive property because there's a plus over there. So you take the first vector and cross it on the left with r prime. Take the second vector and cross it also on the left with r prime. Okay, so remember, the order of the cross product is important. We can't just switch them. Okay, what did we say? R prime is parallel to unit tangent vector, and so the angle is 0. What is sine of 0? This time it's 0. Okay, so therefore, that cross product is just the 0 vector. Okay, so what about this one? Okay, well, we have this cross product, and let's see, what do we have over here? We have r prime of t. Okay, scoot over to the left. Magnitude of t prime, scoot over to the left. And then we have r prime cross the normal vector. Okay, so of course the 0 vector goes away. Take the magnitude now of both sides of this equation. Okay, so we get the magnitude of the cross product. These two are just positive constants, so scalars, so therefore they can just stay out. And we get the magnitude of r prime cross n. Okay, so spell it out. We are going to use the formula for the magnitude of the cross product. It's the product of the two magnitudes times the sine of the angle between them. Okay, so we have the magnitude of r prime right there times the magnitude of n right there times the sine of beta, let's give it a different name, sine of the angle between r prime and n. Okay, but again, r prime is parallel to t is perpendicular to n, so beta is pi over 2, sine of pi over 2 is equal to 1. Okay, so there we go, we have this final simplified form. But we're looking for these two factors. That is our a sub n. Okay, so that's still there. All we have to do is move this over to the left side. Okay, so therefore we have the magnitude of the cross product divided by the magnitude of the first derivative. Yay! All right, so here's our beautiful theorem. We have the acceleration as decomposing as a sub t times the unit tangent vector plus a sub n times the unit normal vector. A sub t is the dot product of the first and second derivatives divided by the magnitude of the first derivative, which also appears in the formula for a sub n, except this time you have the cross product of r prime and r double prime, and you take the magnitude, okay, because both of these are constants, so therefore we want scalars in our formula. Okay, so this is the interpretation of those two components. Okay, the acceleration goes into the curve. Okay, the unit tangent and the unit normal are perpendicular to each other. Okay, the unit tangent, of course, is parallel to the velocity r prime, and if you multiply the unit tangent by a sub t and the unit normal by a sub n, then they will add up to our acceleration. Okay, unfortunately, we have to wait a little bit more to see an example. Don't worry, it's coming. But before we can get there, before we can see the simplified version of finding the unit normal vector, we're going to make it slightly more complex by adding a third vector. Okay, but it's going to be an easy one. Okay, so here's how it works. You have the unit tangent vector and the unit normal vector, which is perpendicular to our unit tangent vector. Okay, so I'm using my right hand. My middle finger is pointing towards the unit tangent vector. My palm is facing towards the normal vector. Okay, so the curve is going this way. Okay, so you can kind of use your hand to like cup the curve. Okay, so now the cross product of the tangent and the normal vector is what we're going to call the binormal vector. Okay, so take that cross product. Okay, and we know that the cross product is perpendicular to both vectors where they came from. Okay, how long is this cross product? Same formula we saw earlier. Take the product of the two lengths and the sine of the angle between them. But t and n are already perpendicular to each other, so therefore the sine is already 1, the product is just 1. Okay, so therefore this cross product is already a unit vector, and we call it B, the unit binormal vector. Okay, so those three together make up a fancy frame called the Fresnet-Serret Frame. I'm not even going to pretend that I speak French. Okay, so here's the curve. Okay, so what I say, pretend that your hand is cupping the curve. The unit tangent vector is pointing towards your finger. The normal vector is away from your palm, and your thumb is pointing towards the binormal vector. All right, so T, N, and B form what's called a right-handed system of vectors because T cross N gives you B. Okay, the standard basis vectors I, J, and K form the simplest examples of right-handed sets of vectors. Unit vectors in this case as well. Okay, why? I cross J is K, right? But there's more. J cross K is also I. K cross I is also J. Okay, what happens if you change the orders? Well, we know that if you take the cross of V and U, you do V cross U instead of U cross V, you get the negative. Okay, so J cross I is negative K, K cross J is negative I, and I cross K is negative J. Okay, so that means that not just I, J, and K, but also J, K, and I, K, I, and J are right-handed sets of vectors. Okay, so I want you to notice something. Start with I, J, K, make I hop over to the end of the list. Then you get J, K, I. Haha, that's called a circular permutation. Okay, all you do is take the first, make it last, and scoot over. Okay, that's called a circular permutation. Okay, do it again. Take J and put it to the end, and now we have Kij. Ooh, so that's all three of them are right-handed sets of vectors. Okay, so of course, if you reverse J and I, then Jik will be left-handed, Kji, Ikj are all left-handed. So our coordinate system with X towards the front, Y towards the right if you're looking from the front, and Z going up, that of course is our right-handed coordinate system. Right, so let's complete our helix example. We already found the unit tangent vector, here we go, and the unit normal vector. This time there is no square root of 2, okay? So we need the cross product of T with N. We put the components of T in the second row. You can leave the 1 over square root of 2 outside and put the components of N in the third row, okay? So take the cross product, 0 plus sine of T for X. For Y, go this way first, negative cosine T, 0, negative cosine T. For Z, sine squared minus minus, plus cosine squared, which is equal to 1, okay? And this should already be a unit vector. Don't forget the 1 over square root of 2. Double check. Sine squared plus cosine squared, 1 plus 1 squared, 2, square root of 2 over square root of 2. We get 1, Okay, so that is, of course, a unit vector, and that is how the Fresnet-Serret frame looks like at several points on our helix. Maybe let's blow this up a little bit. Can we see it better? Yeah, there you go. Okay, so again, you can use your right hand. Make the color scheme is, let's see, this is our tangent vector. Let's see. Okay, here's a better looking diagram. Okay, here's the tangent vector. Here's the normal vector pointing into the curve, and the cross product, that is your normal vector. Okay, you can also see it over here. Tangent vector turn into the normal vector. There's your binormal vector. Okay, so finally, we can find a shortcut method to find the unit normal and binormal vectors. And the trick is, you look for the binormal vector first before you find the normal vector. Okay, so here's how it works. If R prime and R double prime are not parallel to each other, then their cross product in the order R prime cross R double prime is parallel to and points in the same direction as the unit binormal vector. Okay? In other words, if you take the cross product and divide by its length, you get the unit binormal vector very easily. It's very easy to take the cross product of two derivatives without their lengths. No problem at all. You find their lengths later, and then you create the unit vectors. Okay? Now, what did we say? T and then B make a right-handed system. So T cross N is B, and then N cross B is T, and then finally B cross T. B cross T is N. Okay? So after you find B, you cross it with T on the right, and then you get the unit normal vector. Okay, how do we prove it? Okay, in the course of getting our A sub n, okay, remember we took the cross product of R double prime with R prime. Okay, we did two things. We did the dot and we did the cross. If you don't believe me, go back a couple of pages. We got this expression. Okay, so we have the magnitude of R prime, the magnitude of T prime, times the cross product R prime cross N. Okay, but now R prime is, remember, the unit tangent is R prime divided by its length. Okay, so one more time, R prime is just the unit tangent multiplied by the length of R prime. Okay, so therefore, let's replace R prime of T with magnitude of R prime times the unit tangent vector. Okay, and there's what we want. Okay, because unit tangent cross unit normal is your binormal vector. Okay, so that's why we did it. Okay, that's just a scalar, so we can scoot it out. Oh, where did it go? Oh, it joined another magnitude of R prime. So now it's squared. Okay, and we have the magnitude of T prime, and then we have the binormal vector over there. Okay, so what can we say about these two coefficients? Well, they're both lengths, not only lengths, that's squared, so it's already positive. It gets even more positive. That's ridiculous. These two are both positive, so therefore the cross product is a positive multiple of the binormal vector. Okay, so there you go. That cross product is pointing in the same direction as our binormal vector. Okay, so now we can go back to our ugly example, the one with the cubes and the squares, and we can compute our decomposition for A sub t and A sub n, and we can get our unit normal and our unit binormal vectors, starting with the binormal vector. Okay, let's get to work. So we already have R prime at 1, and we have R double prime at 1 right here. So we are going to take their cross product. Okay, so remember how to do that. we need a 3 by 3 determinant. Let's put ij and k on top. R prime goes into the second row, negative 3, 4, 13. Negative 3, positive 4, and 13. All right, second derivative goes into the third row, 2, 10, and 6. Okay, so we are going to create a cross product. Let me borrow this vector over here, and here we go. Let's empty that out. Okay, and we do this in our head. 24 minus 130. Is that negative 106? Whoops, 106. Yeah, 6 and 24 makes 30. Okay, now for J. 13 times 2, 26. Negative 3 minus 18. 26 plus 18. So is that 44? I believe that's 44. Don't worry, we'll check it later. How about for K? Negative 30 minus 8. Oh, something I can do, I think. Minus 38. There we go. Okay, so that is our cross product. So I said check. Oh, do I see a cross over here? Oh, there's one. Ha 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 ha. And here's the second vector. We cross it, and you're going, oh, you're such a cheat. And oh my God, I actually got it correct for a change. Okay, so that is our cross product. Okay, so now we can create the unit binormal vector. Okay, it's just this divided by its length, right? So yeah, length. So we need 106. Keep doing that. Stop that. 106 squared plus 44 squared plus 38 squared, and we get, how much are you? Oh my. Ooh, there must be I believe there should be a 16 in there. So when we take the square root, does that simplify? Come on. Yes. Ooh, there is not just a 4, there is a 36. Okay, so that is our length. So we will take the reciprocal, 1 over 6 square root of 406 times the cross product, which is over here. All right, that's our binormal vector. Okay, so we already checked. That can go away. Okay, so what is the unit normal vector? I always have to do this. TNB, and then NBT, and then BTN. So B cross T is N. How do I get down? N is B cross P. Oh, oh yeah, I already erased it. B, there it is. It's hard when you're old and you can't see very well. Okay, so we will put B in the second row and unit tangent in the third row, but the unit tangent comes from the derivative, which is minus 3, 4, 13, and we have the length, square root of 194, okay? So the lengths can stay outside, right? So we have 1 over square root of 194, that will stay outside, and then this length. So let me put a times symbol just for emphasis right there, okay? And then we're going to take the cross product, okay? So B goes into the second row, and you've seen me do this. All I have to do is that, oh, but wait a minute. The T will go into the third row. So before I obliterate that, scoot down there, haha, take that and scoot up there. Okay, so you know what to do. Okay, 44 times 13 plus this, and then minus minus as a plus, and then plus this. Oh boy, we're going to get big numbers. And then minus this plus this. Okay, so that's going to be our cross product. So you already know that I can do this. So I will do this. And we're going to get as our cross product, who are you? Oh my, yes, that is a large vector. Oh, any chance it's divisible by 6? Ooh, let's see. Okay, I have a gut feeling that it's definitely divisible by 2. But what about by 6? Are you? Ah, bummer. Oh well, it's just divisible by 2. Okay, so in other words then, we can simplify our unit normal vector as, so this product, but instead of a 6, it will just be a 3. Okay, so yeah, we can make this square root scoot next to that one. You can multiply them together if you like into a single square root, but we have this. So yeah, we will divide this by 2. Let me make a copy in case you're looking like wait a minute, what are you doing? So we have this. Okay, so that is our unit binormal vector. Okay, so I'm going to copy that down, and then we're going to go to GeoGebra and continue with the diagram. All right, I hope this works. So let's see. We already have the unit tangent vector here. So I zoomed in. Okay, I changed the what do you call this? The domain of the curve to just 0.5 to 1.5, so that we're very close to the point which is at 1. Okay, so let's draw the other two vectors. Vector A plus, and we have negative 106, 44, and negative 38. And we will divide that by square root of 406. Oh, and there's a 6 beside it. So 6 square root of 406. And let's see how that is. There it is. Oh, okay, I was worried there for a minute. Yeah. It was like, why is it so short? Okay, no. If we turn, I will fix the screen in a second. That will look like the correct length. Okay, so that is our binormal vector, actually. And so we now have our normal vector. So A plus, and we will put that point in, and we will divide by, oh, and back in the numerator. So in the point I will have 362, 746, negative 146. And I also just noticed that everything is even. So actually, if you multiply those two square roots, a 4 will be able to scoot out. So those could be simplified. Okay, I did not simplify it for us. So in the denominator, we have 3 square root of 194 times, I hope it works, 406. Ooh, oh, beautiful. Okay, there it is. There's our normal vector. I'm going to pause the recording so I can move the frame. There we go. That's our TNB frame. Okay, so T is pointing in the direction of the curve. N is pointing into the curve. Okay, so T cross N, and this is our B. So if you turn this way, yeah, those 3 should be perfectly perpendicular to each other. Okay, so there's one more thing I want to do. I want to get the decomposition of our acceleration vector. All right, so we got 2 formulas. For A sub t, we take the dot product of r prime with r double prime at that point, and we divide by the length of r prime, which we already have over here. For A sub n, we take the length of the cross product. Okay, so we already have that over here. We found the cross product over here, and we found its length. 6 square root of 406. So we already have everything we need for a sub n. Okay, a sub n is, in the numerator, we have 6 square root of 406. And in the denominator, we have the magnitude of r prime, which is square root of 194. And I do believe that will simplify a little bit. Will it? Okay. Compute, simplify. Compute and simplify. There it is. Okay, this can combine. It's a little stubborn. Did I mention stubborn? Compute, simplify. Okay, there we go. So it is 6 over 97 times that square root. Okay, what is that approximately? And 8 point something. Okay, so yeah, we saw a picture of a sub n in our last video, and it's kind of long. Okay, so the normal component, not big surprise, it is long. For the tangential component, this time we need the dot product of these two vectors. Okay, so let's set up. We need r prime, which is over here, and we will dot it with, where's my dot? There's my dot. R double prime, which is over here. Okay, so that's already a scalar. We'll get negative 6 plus 4 times 10, 40, plus 13 times 6. I don't trust myself. So there it is, and the final answer is 112. So therefore, our a sub p is, lowercase a sub p equals same fraction, but the numerator is this, 112 over this. Okay, so that is equal to that, yes. And what is that approximately? Oh, also 8, close to 8. All right, so my goodness, so they almost form 45 degrees, okay? The two sides in our decomposition are almost equal, okay? So let us go back to GeoGebra and let's see if our A looks like it is the sum of the two vectors. We will multiply the normal vector by this much and the tangential vector by this much. They should add up together to form our acceleration vector. Okay, luckily most of the ingredients are already here. So this 2, 10, 6, this is our acceleration vector from the other video. So that is our acceleration. Now we will multiply our unit tangent vector by a sub t, which is 8.04. Okay, so this is our unit tangent vector. So all we have to do is scoot over here and multiply by 8.04. Okay. Ooh, okay, nice, nice. I like that. And then similarly, where is our a sub n? It was the last thing we did, which was the 362, this guy over here. So that one, our a sub n is 8.68. 8.68. Keep your fingers crossed. Yes, there it is. There's your decomposition. Okay, so if you look this way, so if these numbers weren't so big, okay, you should be able to see t, n, and b. Okay, but because they're unit vectors, they're small in comparison. But I think this is enough to show you that these two vectors will add up to our acceleration vector. All right, there we go. Not too bad, 45 minutes. So thank you so much for watching this video. We will, of course, continue next time. We are going to do quite a bit. We're going to find the arc length function, reparameterize with respect to the arc length function. Sounds scary. And then we're going to study curvature and the osculating circle and 3 planes, which are going to be containing that point and containing the TND frame, actually. So until our next video, I hope you enjoy the rest of your day. Bye!